Okay, so before I get started on chapter 8, let me sort of give you the punchline. I'll introduce to you an equation, which is what most of the chapter is based on. And so if you understand that one equation, you will understand the slides. Okay. Um, so what we will do is the following. You guys know what this device does. It, prevents you from getting hurt bad. And we'll see what is the basis for the invention of. I'm sorry? I'm sorry? Okay. So we'll see what this does. And okay, here's a squid. And we'll understand how this guy propels himself. Okay, so this squid is at rest. And to propel itself underwater, what it has to do is it's got to squirt out a bunch of water. Okay. And so we'll see what's going on here. Okay. So let's understand the relevant equation. So all this is based on one single equation. So the equation is the following. You guys are all familiar with Newton's second law. It's generally stated like this. Newton's second law is stated as force equal to mass times acceleration. Okay. Now, Mr. Newton actually stated this law not in this form. It was stated like so. Force is change in momentum divided by change in time. Okay. And momentum is defined as mass times velocity of the object. All right, so Mr. Newton stated this is change in momentum is final momentum minus initial momentum. So it's mv final minus mv initial over change in time. All right, now you guys understand the following. If large forces act on you, then you get hurt. Okay, so let's go to the airbag slide. Okay, so in the airbag slide, here's what's happening. So let's say your car is moving at 80 miles per hour. So what is the speed at which you're moving? If you're the same speed, 80 miles an hour. Okay, and now let's say the car is stopped by a wall. Suddenly stopped by a wall. What happens to you? You keep going at 80 miles an hour till you get stopped. And if you didn't have an airbag, what will stop you? The steering wheel will stop you. Okay. Now let's look at this equation. What is the steering wheel? So you will come to rest. This will be 0. Your final velocity will be 0. Your initial velocity is 80 miles an hour. Okay. And if the steering wheel stops you, the steering wheel stops you very fast. Delta T is small when the steering wheel stops you. Okay. And the forces on you are large. Okay. Now, so to make that sure that the forces on you are small, what you want to do is you want to make this large. Your stopping time as large as possible. And that's what the airbag does. Okay. Now there's another thing that it does. Okay, so you'll see lots of examples of this. What you want to do is if you want smaller forces acting on you, you want the stopping time to be large. Okay. So, and here's another thing that the airbag does. Okay, so you see this is a large device. So let me ask, you all have experienced this. Let's say I push my palm with a 15-pound force with my thumb. Now, is this hurting? No. I'm going to push with 15 pounds, same 15-pound force with this pen. Is this hurting? Yeah, it is hurting. Okay, and in fact, so what happened? The force was the same. Okay, in this case, so it's the pressure, larger pressure also hurt. Okay, the same force applied over a smaller area hurts. Okay, so what did the airbag do? Not only did it reduce the force, it also spread that force on you over a larger area. Okay, so less damage was done. Okay, so that's what's happening. Okay. Did you guys understand that? All right. So when you when you are stopped over a larger time, then the forces on you are smaller. Okay. So, and that's the theme. Okay. And let me show you another example. This fella. Okay. This fellow falls out of trees and doesn't hurt himself. Okay. He's a hedgehog. And what he does is when he falls out of a tree, he rolls himself into a ball. Okay. And these quills that are used for defense against predators, they have another use. They are his airbags. Okay, when he falls out of the tree and hits the ground, these guys cushion his fall, and what they do is they increase that time of stopping, so the forces on him are smaller. Okay? So nature uses this equation all the time. Okay? So that's one aspect of the equation that we'll study. Did you guys understand that? Yeah. Okay. So here's another aspect of the equation we'll study. So again, we'll go back to that equation. This is change in momentum divided by the time over which that change happens. Okay. Again, all the secrets are in the equation. Okay. So now let's say this force acting on the system is 0. If there's no force acting on the system, then this is change in momentum, which is so final momentum minus initial momentum divided by that. Okay, so how do you make this 0? If this is 0. Okay, so if there's no force acting on the system, then that means final momentum is equal to initial momentum, because this has to be 0 over change in time. All right, so that's what we'll see. We'll see collisions. In collisions, the momentum before the collision is equal to momentum after the collision. Okay, and we'll see examples of that. Yeah. All right, so that's what most of the chapter is based on. Okay. Did you guys understand that? Yeah. Okay, so let's go over the slides now. Okay, so this last part, when no force acts on it, momentum is conserved. So here is the conservation law. What that means is if, let's say, so if two cars collide and they collide and bounce back and so on, through this entire process, momentum is conserved. That's what a conservation law is. Okay. Energy is conserved, and so on. So there are, in physics, we have conservation laws wherein through the development, through the evolution of a system, this quantity is conserved. Okay. All right. So, so momentum along with energy and angular momentum is conserved. So these are quantities that are conserved in systems. Conservation laws place limits on what an organism can do. Okay. So an organism cannot do anything that would break a conservation law. Okay. So that limits motion and other behaviors that violate a conservation law simply do not occur. Okay. So of course you can't, no matter what you do, you can't break the laws of physics. Okay. That's what we're saying. These laws allow you to analyze situations that would be otherwise extremely difficult to understand. Okay, so let me give you an example. You guys all know this. Okay, you've seen this. So here's an ice skater. She starts off a spin. Okay, and then she'll bring her arms and legs closer together to her axis of rotation. Okay, what happens here? What happens when she brings her arms and legs in? What happens? She spins faster. Okay. Now you couldn't use any other law to analyze this. That would be very hard to do. But what is happening here is something called angular momentum that is conserved. See, this is the angular momentum initially, and that's her angular momentum there. So what happened here was, in the final configuration, in this configuration, her moment of inertia is smaller, and so she's spinning faster. That increase. Okay? So conservation laws allow you to analyze situations which would be very hard to understand otherwise. Okay? So through her entire motion, this quantity, angular momentum, is conserved. Okay. All right. So that's what we mean in that statement. Okay. So conservation. So it'll help us analyze situation. So an ice skater using her arm movements to speed up a spin, or an aquatic organism using jet propulsion to flee from a predator. Okay. So an octopus propels itself by squirting a jet of water in the opposite direction. Okay. So here are two rams headbutting. Okay. And if you watch this on TV and stuff like that, you'll hear a loud sound and all that. Okay? And we have football players having concussions. Okay? So how come these guys don't have concussions? Okay? So again, going back to our thing, our equation, F is delta P by delta T. This is delta P is, this is, in this equation, this is the velocity with this guy's coming initial velocity, and then after he headbutts, he's come to rest. So this becomes 0. Okay? So this is the change in momentum. So this guy comes at him fast, so that's a large momentum change. So if the force on him needs to be small, what needs to happen? That collision needs to last long time. And so what they have is their skulls are soft, and they have this thick, bushy clump of hair that makes this large. Okay, it's like an airbag. And so that's what makes the forces small, and that's why they never come close to a concussion. Okay. So that's so when two objects collide, whether animals or atoms, their subsequent motion is determined by their momentum. Okay, so their momentum. Momentum and impulse help us understand how to limit damage from a collision. Okay. So the rams headbutt at high speed. Thick skulls and a spongy cover protect their brains during these high impact collisions, and they never come close to a concussion. There's another animal that has to face this, woodpeckers. Okay, so each peck of the woodpecker, the forces they have to bear is twice your weight, 1,200 newtons. And they do that millions of times without a concussion. Okay? Part of the deal is their brains are small, and so it's harder to get a concussion. Okay? But anyway, so in many sports, we cause a sudden change in velocity. So when you play golf, see, the ball was at rest initially, and then it goes off at 100 miles an hour. Okay? So here is a sudden change in velocity. And how fast did this happen? The club is in contact with the ball about a millisecond. So you went from rest to 100 miles an hour in a millisecond. In a car, to go from 0 to 100 miles an hour takes you at least 15, 20 seconds. Okay? So we'll talk about situations like this. A collision is a short duration interaction between two objects. The collision between a golf ball and a club may seem instantaneous to your eye, but high-speed photography reveals that the side of the ball is significantly flattened during the collision. It takes time to compress the ball and more time for the ball to re-expand. So collisions they don't happen instantaneously. It does take time. So here's what's happening. So here's the ball coming and contacting this area, and you see the ball is compressed. It's compressed like a spring, energy stored, and when it decompresses, that's what launches the ball. Okay. So if you look at the forces on the ball exerted by this wall, let's say, you see before the ball comes in contact with the wall, the force is 0, and then this force will sharply rise, okay, and then fall down again. Once the ball has left the wall, the force has come back to 0. Okay? And this is very short. So when you're playing golf, the contact lasts 1 millisecond, like I said. If it's a steel ball hitting a steel wall, that's even less. Okay, that's about 0.2 milliseconds. Okay, so this collision lasts a very small time, and the peak force can be as large as 2,000 times the ball's weight. So when you play golf, the peak force on the golf ball could be 2,000 times the weight of the golf ball. Okay? So a collision is a short duration interaction between two objects. Okay? But it does take time. So for instance, a golf ball and a club, you see it's about half a millisecond, the collision time. This is about half a millisecond. Okay? For a baseball and a bat, it's 1 millisecond. Why is that collision longer? Why do you think that collision is longer? Look at for the soccer ball, it's even 10 times, it's 10 milliseconds. So why is this collision longer than this collision, which is longer than that collision? I'm sorry? No, that's not relevant. What might be relevant? The harder the ball, the shorter the collision. Okay, so that's what matters. So in sport, the harder the ball, the shorter the contact time. A collision between two steel balls lasts less than 200 microseconds. That's 0.2 milliseconds, okay? Less than this. All right, so you saw that the force on this ball is like so, okay? And this area under this curve is called an impulse. The area is called impulse. All right, so the difference between a professional golfer and me is a professional golfer, this area is much bigger. Okay? And impulse is equal to the change in momentum. Okay, so initially the golf ball was at rest, so this will be 0. And if you want the golf ball to fly off faster, the impulse needs to be greater. This area needs to be greater. Okay. So for a professional golfer, well, the time still is the same, so their curve is much bigger like that. And for an amateur golfer, it's like that. Okay. So that's the difference between millions of dollars and, no money. All right. So we model a colliding object as an elastic object. What that means is when you compress the ball, you're storing energy in it, and all that energy is released when you lose contact. Okay? So just like when you compress a spring, you're storing energy in it, and when it decompresses, it releases all that energy. Okay? So that's an elastic object. So that compresses. So when we model a colliding object as an elastic object that compresses and expands much like a spring. Indeed, that's exactly what happens at the microscopic level during a collision. Molecular bonds compress, store elastic energy, then re-expand as the object rebounds. Yeah. So a force like this is called an impulsive force. Okay. So a force that lives very short time, and that's what you see in sport when you kick a soccer ball, when you play golf, when you play baseball. Okay. So the force lives a very short time. It changes rapidly. The peak force is enormous. So in any sport, when you are playing baseball, the peak force that the bat exerts on the ball is, like I said, maybe 2,000 times the weight of the ball. Okay? So the peak force is enormous, and then goes back to zero. Okay? So the forces of a collision usually are very large in comparison to other forces exerted on the object. So this force is much larger than any other force, and you can ignore it. Now all other forces. Yeah? So the graph shows a typical impulsive force, rapidly growing to a maximum, then decreasing to zero. Okay? So impulsive forces rapidly change with time. So I already introduced momentum to you. Momentum is denoted by P, the arrow telling you it's a vector quantity, and that is mass times the velocity of the object. Okay. So greater the mass of an object, greater its momentum, greater its velocity, greater its momentum. Okay. And the units of momentum are mass is measured in kilograms, velocity in meters per second. Yeah. So you see momentum points in the same direction as your velocity. So here's the impulse momentum theorem. Again, I mentioned this. So let's say it's a golf club hitting a golf ball. This is the force that the club is exerting in the ball. Okay, and this area under the curve is called the impulse. So impulse is denoted by either I or J, depending on the book you use. Okay. So I'll say I for impulse, and that's equal to area under the curve. Okay. And what this says is, okay, so this area, oftentimes it's very hard to measure the force in detail. So all we are interested in is the average force that is acting on the object, the average force that the club exerts on the ball, the average force your foot is exerting on the soccer ball, the average force your hand is exerting on a volleyball when you spike the ball, and so on. Okay, so this is the average force, and delta t is the time over which that force acts. So average force times time is equal to change in momentum. Yeah. So greater the change in velocity, greater the momentum change. Greater the impulse, greater the change in velocity. Okay. All right. So we'll apply that to an example, this example. Okay, so let's say you want to jump high. Okay, so you start off at rest. So to jump higher, what do you have to do? You have to launch at a greater speed. Okay, so you have to launch at a greater speed. That means this guy needs to be bigger. Okay. Now the force that your muscle can apply, there's a limit to that. So there's a limit to that. So if you want to jump higher, then you need to apply that force for a longer time. Okay? And so here's what happens. Animals that can jump higher, they have longer legs. So they can push off the ground for a longer time. Okay? So you see here's a frog, and if it's longer legs, the leg is unfolding over a longer time. It's applying that force over a longer time. And so it can apply a greater impulse and have a greater velocity with which it launches. Okay? All right, so there's a maximum force that muscles can exert. Hence, to impart a greater impulse, the time over the force acts must increase. Okay? So the time interval during which the force is exerted can be greatly increased by having long legs. Okay? So frogs have long legs. Can you think of any other examples that have long legs? Kangaroos do the same thing, okay? And so on. So, and you guys do it too, okay? So even with the given legs, if you want to jump higher, what do? You bend lower, you're unfolding for a longer time, and you're applying a force for a longer time, okay? So that's what's going on. Okay, so Newton's second law was really expressed like so. Force is equal to change in momentum over change in time. This form of Newton's second law is really a special case. This is when the mass is not changing. This will let you deal with cases where the mass of the object is changing. So Newton formulated his second law in terms of the momentum rather than acceleration. Okay? Not like this, but like that. Okay? This statement of the second law, saying the force is the rate of change of momentum, is more general. It allows for the possibility of mass of an object changing, such as an octopus losing mass as it expels water, or the case of rocket flight. You know, a rocket is mostly fuel. It's more than 90% fuel. Okay, this rocket, in the span of about 5 minutes, loses 90% of its mass. Okay, so to analyze this, you have to use this equation, not this equation. When you drive your car, you can drive your car for 2 hours, and you lose less than 1% of your mass. The gas in your car weighs less than 1%. Okay? So while you're driving your car, your mass doesn't change much, so you can use this equation. But if you're flying a rocket, you have to use this equation. Okay? All right, so here's another example. You guys have seen this competition. And what is the idea of this? You're throwing an egg back and forth. And the winner is whoever can throw it from the furthest, right? So how do you prevent the egg from breaking? What will break the egg? A larger force will break the egg. Okay? So to prevent it from breaking, you have to make sure that the force on the egg is small. Okay? When you throw the egg, well, it has speed, and you got to stop it. Stop the egg as you're catching it. So M initial. Okay, you want to stop the egg. It had an initial velocity, so the further you are, the greater its initial velocity. Okay, so to make sure that the force is small, you have to stop it over a larger time, like we said. Okay? And so what is the strategy? So when somebody throws the egg at you, you're catching it and you're pulling your hands inwards. Okay? And that's how you're extending the time of stopping. Okay? If you stiff arm and try and catch the egg like that, what you'll have is not a whole egg, but an egg ready to be made an omelet out of, you know. So that's the strategy. Again, see, like I keep saying, the equations have all the secrets. Okay? So to apply a smaller force, you have to make sure that the collision is happening over a longer time. Okay. The winning strategy is to pull your hands inwards towards your ball while catching the eggs so that it slows down over the longest period of time. Okay, and you do this in all sport. When you're catching a baseball, you know, you don't hold your mitt and hold your hand just like that. That'll hurt. Okay? You can watch a catcher and they're always pulling their hands back. Okay, so making sure that the forces are smaller. Okay? That's how you extend the collision time. Okay, that's how airbags work. Okay, so the inverse relationship between force and time has many applications. So the inverse relationship between force and time has many applications in preventing injury. I guess seat belts and airbags, that's what they're doing. They're increasing time. That's what a bike helmet does. It's filled with crushable material that in an accident brings the rider's head to rest more slowly, again increasing the time. So lengthening lengthening collision times reduces impact forces and saves lives. So these Rocky Mountain bighorn sheep, they have thin, flexible bones in their sinus cavities that will, compress or deform when they collide. And again, their job is to increase the collision time, the stopping time. Spongy masses between a double-wall cranium stretch out the collision time during which the brain comes to rest in roughly a quarter of a second. Okay, so when they collide, it comes to rest in a quarter of a second. So this is a quarter of a second. That's 250 milliseconds. No, that's 250 milliseconds. Remember, a golf ball collides in 1 millisecond. Okay? So this is a much longer collision. The impacts, while dramatic, are not forceful enough to cause brain injury. Okay? So that's what happens then. Okay, so here's a hedgehog. The spines of the hedgehog help protect it from predators, but they serve another function as well. So they act as the airbags for the hedgehog. If a hedgehog falls from a tree, which is not an uncommon occurrence, it simply rolls itself into a ball before it lands. Okay? And so that cushions its fall. All it's doing is increasing the stopping time, and the force on it is small. Okay? Its thick spines cushion the blow by increasing the time it takes for the animal to come to rest. Okay? Increasing this time. All right, now we'll look at the second application of that equation. Okay, so again, the net force this is Newton's second law. The net force acting on it is change in momentum divided by time. The forces are external forces and internal forces. Okay, so for instance, when these guys are colliding, these are the internal forces. And you see the internal forces are always equal and opposite. So they'll always add up to 0. Okay, so the net force really acting on a system is just the external force. External force acting on the system is change in momentum of the system divided by change over time. Okay, so now we'll talk about if the external force is 0, then the change in momentum over time is 0. And the only way this can be 0 is when this is 0. So PF, the final momentum, is equal to the initial momentum, has to be equal to the initial momentum. All right, so when no external force acts on a system, the momentum of the system is 0. Final momentum is equal to initial momentum of the system. So what we are saying is, in this case, the momentum of these two guys before they collide is equal to the momentum of the two guys after they collide. Okay, so that's what that means. That's what is happening for a rocket, for instance. Okay, so here's a rocket that is at rest. So if the rocket wants to go forward, what it has to do is it has to expel gases backward. Okay, so its momentum, initial momentum was 0, and the momentum of the rocket and the gas, also has to be 0. Okay, so to propel forward, okay, if you want to go forward, you have to throw something backwards. Okay? You can do this on a, for instance, you can go wear skates and be on a frozen pond, and if you keep throwing objects forward, you'll keep going backwards, and that's a rocket. Okay? And a squid uses that strategy. That's what a squid does. That's what an octopus does. That's how they'll propel each other. Okay? So when a rocket, now of course, so this is true if you were in space where there's no forces acting on you. When you take off from Earth, there's a force of Earth's gravity which slows you down, so you can take that into account. But that's essentially the idea. Okay? So here's a problem showing you a simple calculation. Okay? So here's a car of mass m, So it's going with an initial velocity vi, colliding with this car whose mass is 2m and it's at rest. So the initial momentum in this collision should equal the final momentum. The initial momentum is mv. Okay, so the momentum of this guy, mv initial, plus the momentum of this guy, which is 0. And that should equal, so after collision, if they stick together, now you can find the speed at which they're going. Okay, so this is the initial momentum. The final momentum is, now they're sticking together, so their mass is combined, and that should equal the final velocity. So the final velocity is m divided by 3m times initial velocity. Okay, the final velocity, this is 3m. Okay, m times v initial divided by 3m. Okay, so the final velocity is 1/3 v initial. So here's something we calculated using conservation of momentum principle. All right, so there's something neat about it. Okay, so if these two cars, if one collides with a car that's twice as massive and it was at rest, these two combined cars will go at 1/3 the initial velocity. No matter what they're made out of. I didn't tell you what material they were made out of. Okay? So if they stick together, that's the speed they'll go at. Okay? So the conservation law tells you exactly what will happen afterwards. Okay? This combined object cannot go at any other velocity. Okay? That's what I see. This is the principle that the squid uses. So initial momentum, here's the initial momentum. Here's the squid at rest. Okay? And somebody has come to eat it, and so what does it have to do? It has got to run away fast. Okay? So what it does is, so here's the final momentum. Okay? So what the squid does is, it's got a store of water which it squirts out, and then so it propels forward just like a rocket. And here's an amazing number, absolutely amazing number. So the amount of water it stores is 100 grams. 100 grams is about 1/3 of a soda can. Excuse me? Hello there? Can you hold up your Red Bull? How many mLs is that? Can you look at, is it 350 ml?
It's 250.
I'm sorry?
250.
Okay, so half of that. Half of that is stored in the squid. And it squirts it out at 45 meters per second. 45 meters per second is roughly 150 miles an hour. It's squirting out water at 150 miles an hour underwater. Okay? And it propels forward at 3 meters per second. 3 meters per second is 1/3 the speed of Usain Bolt. Okay, so that's the speed at which it can launch forward. Absolutely amazing. And so, it has to be aerodynamically shaped too. It can't be flat like that. If it were flat like that, there would be too much drag and it would stop fast. Okay? All right, so squids rely on jet propulsion when a rapid escape is necessary. The 1.5 kg squid at rest has 100 grams of water in its mantle. Okay? Strong muscular contractions eject water at a remarkable 45 meters per second. Okay, so that takes a lot of energy. Okay, you're not going to do that for play. When are you only going to do that is if a shark is after you. All right? So, and so again, you use momentum principles to solve this. Initial momentum is 0, initial velocity is 0. Okay, so all right, so the final momentum is, okay, mass of the squid times mass of the water. Initial momentum is 0. Okay, so mass of the squid is 1.5 kgs, 1.5 kgs, and so velocity of the squid, mass of the water is 0.1 kg. That's again, you don't have to know all the details, you just have to know the answer. Okay, mass of the water is 0.1 kg, and you squirt it out in the opposite direction, and that's why the negative sign, and that should equal the initial momentum, which was 0. Okay, so the velocity of the squid is 0.1 times 45 is 4.5. 4.5 divided by 1.5, which is equal to 3 meters per second. So the squid is jetting off at 3 meters per second. Usain Bolt runs at 10 meters per second. Okay? So that's the speed at which it takes off. So uranium-238, it's a radioactive element. Uranium-238, so you can see that on the chart there. Where is uranium? Okay, so on the last row, the last black element, uranium, 92 is the atomic number, meaning 92 protons. Okay? And 238 is the number of protons and neutrons it has. So this isotope of uranium, it radioactively decays spontaneously. So it'll break up into 2 pieces. So if this guy was at rest, there's a big piece that goes in this direction, and the small piece goes in this direction. Now this momentum was 0, so here's another thing this momentum conservation says. These guys have to go exactly in opposite direction, these 2 pieces. For instance, this guy can't go in this direction and that guy can't go in that direction, because then the momentum would be non-zero, the final momentum. So no matter what, so when this thing breaks up, the 2 pieces have to go exactly in opposite direction. They can go in any direction, but they are always exactly 180 degrees apart. Okay? And the momentum of this guy has to be exactly opposite to the momentum of this guy, because then they 2 add up to 0 momentum. Okay? So this guy actually breaks up into the 2 pieces. It breaks up into this is a thorium nucleus. Okay, a thorium nucleus has 2 less protons. So thorium is on that periodic table, it's the one on the left, two places left. So uranium is 92, thorium has 90 protons. Okay? And this is called an alpha particle. That's a helium nucleus. That's 2 protons and 2 neutrons. Okay, so your uranium nucleus at rest, when it decays into these 2 pieces. Okay, and they have measured speeds of these guys. This guy goes at 1.5 times 10 to the 7 meters per second. And this guy goes at 2.56 times 10 to the 5 meters per second. So this guy is roughly moving 100 times slower. Okay, and so from momentum conservation, you can calculate their masses. Okay, so initial momentum is 0, which should equal final momentum, should equal 0. Okay, final momentum is m1 times v1 plus m2 times v2. This should be 0. v1 is this speed, v2 is this speed. Okay, so this would be negative of that. And also their combined masses should be equal to the mass of the uranium-238 initially. Okay, so between this equation and this equation, knowing the velocities, you can calculate the masses. Okay, so you can identify these pieces, and that's what this problem shows you. Okay, and again, like I said, you just have to know that. Okay, so uranium decays into thorium. Like I said, that's on the periodic table, and the alpha particle. So they are the combined masses. M1 is 234. Okay, 34 units. So uranium has a mass of 238 units. M1 has 234 units. That's the mass of the uranium. And M2 is 238 minus 234, 4 units, atomic units. All right, so when uranium breaks up into two pieces, the decay products are thorium and alpha. Okay, this momentum conservation analysis lets you calculate the masses, but you don't know what the chemical is. Okay, so as we learn from a momentum, all we learn from a momentum analysis is the masses. Chemical analysis show their daughter nucleus is thorium with atomic number 90. So to identify this piece, you really have to do chemical analysis. Okay, from the momentum analysis, all you can find is its mass. But different isotopes can have the same mass. Different chemicals can have the same mass. So they're different isotopes. You have to do chemical analysis to find what that is. Okay. All right, now we'll talk about another kind of momentum, angular momentum. So angular momentum is when you're spinning. Okay. Linear momentum is when you're moving, when you have translational motion. Okay. So when you have a this is linear momentum. And when an object is spinning, so let's say it's spinning with an angular velocity omega, angular momentum is denoted by L. And this is the moment of inertia. I is the moment of inertia times angular velocity. Okay, we saw that in the case of the spinning skater. Okay, so what happens is, so here's the moment of inertia, and there's the angular velocity, and this angular momentum remains constant, is conserved. So if you can decrease your moment of inertia, you can increase your angular momentum. Okay, and that's what happens in many situations. So you're decreasing your moment of inertia, and you're increasing your angular velocity. So the skater who's spinning faster, that's what she did. She decreased her angular momentum. Okay? I mean, moment of inertia. So angular momentum is I times, okay? And here's the second law. The torque, external torque acting on an object is equal to rate change in angular momentum divided by the time over which that change happens. Okay, so now if this is 0, then L final minus L initial equal to 0. That means that this has to be 0. If there is no torque acting on the object, then this has to be 0. So angular momentum is conserved. Okay. So let's see an example of that. All right, so you guys have seen hurricanes, okay, and the air mass is going the fastest near the eye. What happens is, as the air mass comes closer to the eye of the hurricane, the moment of inertia is mass times how far you are from the axis of rotation, how far you are from the axis of rotation. So as the air mass gets closer, R decreases, this is decreasing, okay, as R decreases. And so as the air mass comes closer, it's going around faster. Okay? So as the air mass gets closer, the moment of inertia is decreasing, and it's going around faster and faster. Okay? Just like a skater. That's what happens. Okay? The angular momentum of this air mass is conserved. Their speed must increase as they approach the center, leading to high wind speeds near the center of the storm. Why does the air mass go towards the center, toward the eye? Do you guys know? because the I is a low pressure area, and air mass will move from high pressure area to low pressure area. The as air masses from slowly rotating outer zones of the hurricane are drawn toward the low pressure center. Okay, so they move toward the low pressure center. Their moment of inertia increases. Okay, just like that. So that's what's happening here as well. As so when our arms are far apart, see the moment of inertia is this is various body parts and the distance from the axis of rotation. And so as this reduces, moment of inertia reduces. So as she brings her arms in, this is reducing and the moment of inertia is reducing. So in this configuration, her moment of inertia is smaller, and so her angular speed is bigger. And look at this, world-class skaters can increase their angular speed of spin by a factor of 5. So world-class skaters can spin 5 times faster. Okay? And of course, in this thing, what do you want to be? Do you want to be tall or short? If you're tall and have lanky arms and legs, you can bring them closer together. Okay, you can change your moment of inertia more. That's why you can spin faster. Okay, so having long limbs helps. Okay, so that's what's happening here as well. Okay, in this diving competition, okay, in some competitions, what you have to do is you jump off the diving board, and some competition you have to spin twice before you enter water, and in some competition you have to spin 3 times before you enter water. So how do you do that? Okay, so here's what you do. So when you jump off, you're leaning forward, and you see you push off the board. When you push off the board, this force of the board, the push has to be greater than your weight, because you have to launch, you got to give yourself some speed. And in addition, okay, so let's say, so I'm going to draw sort of a wider picture. So here is the push off. Here is your center of mass behind your belly button. So what you do is this pushing force, what it does is it gives you a spin. So it does 2 things. This pushing force launches you up, and it also spins you. So it gives you some angular momentum. And so once you're in the air, only gravity is acting on you, and that doesn't give you any torque around the center of mass. And so your angular momentum is conserved. So through this entire motion, L is constant. Okay, so once you leave, the push gave you a certain amount of angular momentum, and through this entire motion, now the angular momentum is constant. Okay, so you play with this thing. Angular momentum is moment of inertia times your angular velocity. So if you want to spin faster, you just reduce your moment of inertia. So if you want to spin faster, you tuck in. And when you want to stop the spin, what do? You untuck. Okay? And so if you want to spin 3 times, you are tucked in for a longer time. You spin as long as you want, and then you untuck and you fall into the water. Okay, and in this competition, you want to fall into the water straight in. Okay, even as you're entering water, you're turning, so you just have to time it right so it appears like you're going in straight. Okay. So once clear of the board, her weight is the only force. So once clear of the board, her weight is the only force acting on her. But she experiences no torque about her center of gravity. Thus, her angular momentum is conserved. So through this entire time in air, her angular momentum is constant. Okay. And so you change your spin rate by changing your moment of inertia. You tuck in, you reduce this, and you can increase that. You untuck yourself, you increase that, and that'll reduce. Okay? So that's what's in your control. So initially the diver's rotation speed is small. Initially this is small. However, going into a tuck position significantly decreases her moment of inertia. Going into a tuck position, it reduces that. The faster spin allows her to complete a rotation or two or three or whatever she wants to do. Okay. Divers are still rotating as they enter water, and it's very easy if the timing isn't perfect to over rotate and not enter vertically. Not only do you lose points, it hurts too. So you gotta make sure that you get it right. Okay. All right, guys. So that